Okay, today we're talking about section 3.4, and in section 3.4 we're going to be solving the last, or giving the last piece of the puzzle in solving ay double prime plus by prime plus cy equals 0, and in this case when b squared minus 4ac is equal to 0. So remember that the solutions to the characteristic equation from the quadratic formula will be given by that, right? So if b squared minus 4ac is equal to 0, that means this part's equal to 0, then your r is just going to be a single real value minus b over 2a. And so far from our ansatz, we know that we can write one of our solutions then as e to the minus b over 2at. So then the question is, find y2 so that y1 and y2 form a fundamental set of solutions, right? Because we know we need two functions for our second order differential equation. Good. Now I'm going to tell you what the answer is first, and then we're going to prove it. So the answer is going to be that y2 of t can be found just by multiplying the solution by t. Okay, and now we're going to prove it. And the proof we're going to spend a little time with, because we're going to learn a new technique, and then we're going to do some review of an old technique. Okay, and so both techniques will depend on the following proof. The idea is that given y1, right, as one solution to the second order differential equation, find a second. Let me emphasize that this is for L of y equals 0. Find a second. This may sound familiar because method 1 is to use the Wronskian in two ways. Do you remember that? So how did that go? So I'm just going to briefly describe that one. We used Abel's theorem with the differential equation to compute the Wronskian in one way, and so remember to divide by a first. And so remember that by Abel's theorem we can write the Wronskian of y1 and y2 as c e to the minus integral p of t dt, which in this case is going to be minus b over a times t, right? Good. What's the other way of, so this is the first way of writing the Wronskian, maybe 1a. The second way of writing the Wronskian is using the definition, b, using the definition, right? We have that we're using e to the minus b over 2a as our first solution. Differentiate it. Right, then write down our derivative, or our determinant is what I meant to say. Minus minus will give us a plus. Good. And now what do we do? These two things should be equal to each other, right? This should be equal to that, and that gives us a first order differential equation in y2. So just to write that down, we'll have e to the minus b over 2at y2 prime plus b over 2a e to the minus b over 2at. Oops, that was just a, was that a 2at? Yes, that was a 2at. Because on the other side you have to be careful, right? Because that's not 2a in the denominator, that's just a single b over a times t. Good. So then simplifying that, you're going to end up with y2 prime plus b over 2a e to the, oops, I lost my y2, is equal to c times e to the what power? So we're taking b over 2a minus b over a, right? So that's going to be a minus b over a. Oh, 2a, sorry. And so this is going to be minus b over 2a t. Good. And now this is a really simple differential equation to solve. So I will let you solve that. And you should see that y2 can be taken to be t times e to the minus b over 2at. And that finishes that. Good. Okay, the second technique that I wanted to talk about today is a new technique. And the new technique is called reduction of order. And so what's the setup to this? We're given y double prime plus a generic differential equation, but it is homogeneous, that's important, and one solution, y1 of t. What we want to find y2 of t. Okay, and so the way the reduction of order works is we assume a new ansatz y2 we assume to be v of t for some unknown v times y2 of t. Oops, sorry, y1 of t. So we assume that our unknown is a multiple of y1, but the multiple is a function of t. Okay, so how are we going to find y2 then? Is we're going to substitute this expression into the DE and simplify to see what we get. Okay, so in order to do that I need, let's see, y2 prime is going to be v prime y1 plus v times y1 prime, and y2 double prime is going to be v double prime by y1 plus, let's see, this looks like 2v prime y1 prime, right? Plus v times y1 double prime. Okay, and now substitute those expressions into my differential equation, and we get y2, well, maybe okay, I'll rewrite it. Maybe I'll pause it here so you don't have to watch me. Okay, so I've just written down p times y2 here underneath my y2 double prime, and I've got my p, so I'm using this expression right here, right? I'm writing it down in this row, and then adding q times y2, and if you add things straight down, things are going to drop out. So let's take a look at this first stuff here that you're adding together. Notice the v factors out of that, and so if you just look at this expression, which you're multiplying together, is v times y1 double prime plus p times y1 prime plus q times y1. What does that look familiar to you? It should, because we said that y1 was a solution to this differential equation, right? Therefore, what's the quantity here in parentheses? This is equal to 0. Good, so this drops out, and so what you're left with then is, we want the left hand side to be 0, right? And what we're left with is v double prime y1 plus 2y1 prime plus py1 times v prime, right? Now notice that y1 is known. Therefore, this is a known function of t. Known function of t. This is a known function of t. Right? And so what do you have here? You could think of this as a first order differential equation, right? So you could let w be equal to v prime, and then this differential equation becomes w prime, well, y1 times w prime plus 2y1 prime plus py1 times w equals 0. And now this is a linear first order dE in w. Good. So I would encourage you to try this method out in this proof. I'm going to leave that as an exercise, actually. So again, this is called reduction of order, and the way reduction of order works is that you're given a linear first order differential equation, a second order differential equation, and one solution, and you're trying to find a second solution, and that second solution, by the way, you want y1 and y2 to form a fundamental set. Okay, good. And then the way to do that is through this ansatz, which is not intuitive at all. But it works. Okay, and so see if you can prove then that the y2 in this case actually gives you what you want. Good. So in the next video we're just going to try a couple of examples.